All right, today, by the time you walk out of here, you should be well versed in the difference between these two concepts. We're going to compare and contrast two kinds of rates of change. One is called the instantaneous rate of change versus the average. If you have already taken a physics class, these words will be familiar to you. If not, if you're in physics right now, you'll see a lot of crossover between those phrases. Visually, we're going to talk about secant versus tangent and the difference in those two types of slope. And so we should walk out of there with the compare and contrast of those two concepts. This is foundational to being able to do calculus. So let's start with average. The average rate of change is defined in this way. The amount of change divided by the length of the interval. The amount of change you experience divided by the length. And now if it's a physics question, it's the length of the interval of time that you divide by. That's why all of our units have time. And when you say miles per hour, meters per second, millimeters per minute, the time is always the bottom part of the equation. Morning. Thanks. We also call that the secant line of a curve. So let's say the amount of change, that is the change in y values, is divided by the change in the x values. And this really connects to units. Whatever units the y values are measured in, whether it be miles, meters, inches, centimeters, gallons, divided by whatever units the x is measured in. So whether that is seconds, hours, months, years, days, it's a unit of time. Just disappeared. So how do we figure out the change in y values? A change in a y value is a subtraction from one y value to the next. And so we say f of b minus f of a. F is the y values, and so we take the difference or the subtraction between the two of those. We divide it by the difference in the x values, which will just be b minus a. What does that look an awful lot like? What formula that you've memorized before? Yeah, it's exact, and it is the slope formula, y2 minus y1 over x2 minus x1. It's exactly the same. So this is the definition of the average rate of change. So anytime someone says, find the average rate of change, this is what you do. You're calculating the slope between any two given points. You don't need calculus to do that. You've been doing this since Algebra 1. Find the average rate of change over the interval for that parabola function from -2 to 4. Okay? You don't need calculus for this. You don't even need a calculator. So we would be finding the average rate of change, the ROC, is going to be f of the y value at 4 minus the y value at -2 over 4 minus the x value of -2. So you're going to set it up for me so I know you know what the formula is, and then you're just going to proceed to do the mathematics on that. So this will be 2 times 16 minus 3 times 4 plus 7 minus 2 times -2 squared plus 3 times -2 minus 7. So I am subtracting the difference of the y values, and then the denominator will become 4 plus 2. So it just becomes arithmetic for you to do. Doesn't take calculus. It doesn't take any, super advanced things, as long as you know how to multiply, subtract, etc. Yes, ma'am? So you could do a couple things. So you could put parentheses here around all of this, since that's the second one, and then you would have, it won't let me erase. Let me see. I always have trouble with this, but I usually don't. I usually just distribute it as I go. So I've already distributed my negative to all those terms. So I'm going to have 32 minus 12 plus 7. So 32 minus, yeah. 2. Yes. minus 8 minus 6 minus 7 all over 6. So the minus 7 and the plus 7. So then we'll have 20 minus 14. 6 over 6 is 1. So the average rate of change by definition then is 1 just by doing math and subtraction. Again, this doesn't require calculus, okay? So this is old stuff. All right, what do you need calculus for? In calculus, we want to define the rate at which something is changing not over an interval of time, but at a particular moment of time. So not over a whole span of 10 seconds, but what's happening right at second number 4, or something instantaneous. So rather than being an interval of time, it is a single unit of time. And so we define that as how the rate is changing with respect to x at a particular value, a. Not a and b, just a. And we call that the tangent. Oh, nope, I already had the word. The slope of the tangent to the curve. So it's not connecting 2 points to make a slope. It's not slope from point A to point B. It's the slope just at point A. What would the slope be at that very moment? We call that the instantaneous rate of change. So you've got average versus instantaneous. So the definition of that. Since we don't have 2 points, we don't have a point A and we don't have a point B, we've got f of I don't know minus f of A over something I don't know minus A. So it used to be f of B minus f of A over B minus A, but we don't have a second point to work with. So we have to use an arbitrary value, x, so it's f of x minus f of A over x minus A, and it has a limit. Now I want you to help me think through this a minute, what we're going to have for our limit. Okay, can you picture on a function point A and point B? Right? Okay. In this instantaneous, we're only allowed to use 1 point. So we have point A and we have point X. But if we're only allowed to use 1 point, what has to be true about point A and point X? They have to be the same point. Because we're only allowed to use 1 point. We can't use a point A and a point B, which are far apart from each other. We have to use a point A with a point X that is so incredibly close to point A that they're practically on top of each other. Now, can we use point A exactly? Can we use A and A? What would happen in the subtraction of the denominator if we used A and A? We get 0, which we can't have. So x has to approach A, but not touch A. All right, and so we use limits and we say x is approaching A. This is the formula for the instantaneous rate of change. And now we're talking about limits, which is why we need calculus for it, because limits are something that's the foundation of calculus. So you have average, which is A to B, 2 distinct points. You have instantaneous, which is A to X, but A and X are approaching each other. They're practically the same thing. Approaching, but not exactly the same thing. All right, so let's look at that again. We just want to compare side by side, average versus instantaneous. If you're talking about average, you'll be talking about f of B minus f of A over B minus A. You will be talking about a secant slope between 2 distinct points, point A and point B. If you need help picturing that, think of it like this way. Just draw some kind of curve and go from point A to point B and connect the secant between the two. That's a secant slope. It goes from one to the other. It's not curved. It doesn't follow the curve. It just connects one to the other. That is average. And then if we're comparing that to instantaneous, we have f of x minus f of a over x minus a, where the limit is approaching a. If you fail to put limit when you're talking about instantaneous, then it's not instantaneous. It reverts back to average. So without the limit in front of it, it's just an average and it's not an instantaneous. And so yeah, then you'll be marked down. Oh shoot, they don't know the difference between instantaneous and average. This is called the tangent slope. Along one particular point instead of two. So if you need help visualizing that, it might be that same curve where you have A at the beginning and B. But if we're finding the tangent slope, it would be if we stayed on that slope what A was and we went just a straight line from there, what would that look like? And it would look like that, because A has a steeper slope as opposed to following the curve to B. If I just shot straight off, I remember when Angry Birds was really popular, it was like, this was great because you could talk about shooting and what would it be, what angle, what tangent line would you have as you go across from there. All right, so let's do some math on it. Given the parabola, x squared minus 2, find the instantaneous rate of change at the point -1. So what would the tangent slope be just at that moment? So then you're going to set this up as the limit as x approaches -1. That's what I'm looking for. So this will be f of x minus f of -1 over x minus -1. Again, if you don't have the limit notation, then you're just doing average. So make sure you keep that limit notation there. Every time you work, you're going to precede your work with an equal sign and the limit. And we're going to say, all right, f of x is x squared plus 2. That's the function. And then minus, and I need to know what f of -1 is if I plug -1 into the function. All right, what do I get when I plug -1 in? 3. Over x plus 1. So then we precede our work again with good equal signs, and we say, oh, I have x squared minus 1 in the numerator and x plus 1 in the denominator. Yeah, Zach?
Should the result for f of parentheses?
You could do, you mean like that? I mean, if you had a negative number, you'd probably want to put it in parentheses so that when you combine it with the subtraction, then it will become a plus. So I usually don't do it for a positive number. I do it for a negative. Okay, can I plug -1 in here? Yeah.
Does the limit have to have parentheses?
The whole thing? The division line is what's called a grouping symbol. So that would also act like parentheses. So if you have division, you can... Yeah, then you have to have some kind of grouping symbol. So the division bar does act as a grouping symbol. It's never wrong to have parentheses, okay? But it is wrong not to have them when you need them. Right? Sorry, I know that's ambiguous. If I plug -1 in here, I am going to get 0 over 0, which we know is an indeterminate form, which means we need to go back and do one of the things we would do with indeterminate forms, which is factoring in this case. So we want to proceed with limit notation because I'm still doing algebraic techniques. And we factor this into x plus 1, x minus 1 over x plus 1. That only works for polynomials. This is, but it's not a proof. A rule is not a proof. You don't know that yet. You only learned it because Mr. Edlin told it to you.
That's pretty true.
All right, and then we're going to plug this in, and we get -2. So what does this mean? It means at the parabola, if you were sitting at the point -1 on the parabola, the slope at that moment would have -2. Will it ever be -2 again? Not on a parabola. A parabola has a different slope at every single point of its entire all real numbers domain. It will never be -2 again. It is only going to be -2 at this instant. If you move a little bit off of -2, either be more steep or less steep. In fact, sometimes it's even going to be positive because the parabola is going to curve back in an upward direction. It will never be -2 again. This is the moment. This is called the instantaneous rate of change. Okay, let's try another one. Find the instantaneous rate of change for the volume of a cube at 3. What's missing from this problem is a formula. But what's implied in this problem is a formula. There is no f of x right now, but we imply that you are mathematically astute enough to know how to find the volume of a cube. So you're going to have to write that yourself. The volume of a cube of side x is what? Length times width times height, which would be x times x times x. And so this would be x cubed. Don't introduce new variables. If the variable was given to you as x, please use x. Okay. Well, a cube is a rectangular prism, but a cube has all three sides the same. Mm-hmm. All right, so that's the formula you'll be working with. And if you want to find the instantaneous rate of that, you'll be doing the limit as x approaches 3 of v of x minus v of 3 over x minus 3. So you're going to have to know a little bit of your geometry rules before you go and jump into your calculus. So then we work through this. The limit as x approaches 3, the function for the volume of a cube is x cubed, minus v of 3 is 27 over x minus 3. And again, if I plug 3 in, I will get 0 over 0, which is an indeterminate form, which means I must be able to factor this somehow. Last week, we saw the difference of cubes in our homework. Does anybody remember from last week how to factor the difference of cubes? Weston's going to try? Okay.
X minus 3.
Okay, I'm going to stop you there. Yes, he's right. Kind of a dead giveaway that it has to start with x minus 3. Why? Can you think ahead? What do you want to happen? I want to reduce, okay? Not cancel, but I want to reduce. So x minus 3 is going to be a good thing for me to have, and it is. And I'll give you a hint too. All of your homework factors perfectly. Yay. And if it doesn't, you're not doing it right, okay? So all of the problems right now factor beautifully. All right, Weston, keep going.
X squared minus 3x plus 9.
How do you do? Should be a plus right here. The only it would be a minus if the sum of cubes, then it would be a minus there, but we need that to be a. Okay? Again, how does that still look okay? Okay, still something's missing. Look at what would happen if you take the 3 in the first parenthesis multiplied with the 9 at the last parenthesis. What would you get? I get positive 27. What am I supposed to get? Negative 27. This is the difference of cubes, which means that one has to be positive also. You gotta have, it's gotta work out to the difference of cubes. All right, and then over x minus 3. Okay, great. Now I can happily reduce. So we'll have the limit as x approaches 3 of the grouping, parentheses, x squared plus 3x plus 9. Now I can plug the number 3 into this equation. So I'm going to get 9 plus 9 plus 9, which is 27. What that means is on this cubic, at this moment, the slope will be 27. Pretty steep slope. Will it ever be 27 again? On a cubic, yes. If you know the shape of a cubic, there will be a point of symmetry that has this same slope, but only one other spot. Okay, any questions so far? All right, let's keep going. All right, so here is, again, the visual I tried to draw for you. This is a secant line. A secant line connects two distinct points, A and B, to each other. So I just need you to understand that there's a gap between the secant line and the actual curve. There's going to be all this space in between. That's why it's an average and it's not an exact value. As opposed to a tangent line simply skims off one point and has nothing else in common with the function other than that single one point. They share a y value and they share a slope at that one moment, and then they just continue on the trajectory of the line with whatever the slope was at that moment. Yeah?
So, as long as the function is continuous and it doesn't have an interval, that means there would be infinite tangent lines among the point?
No.
No, sorry, not among the point, but there would be...
Every single point would have a different tangent line.
Yeah.
Mm-hmm. Every single point will have a different tangent line because they all have a unique point. Because they pass they pass the vertical line test, so they all have a distinct point, and they all have a distinct slope.
Would that mean even if it's in an interval, would there be infinite?
Mm-hmm. Okay, so this is the definition of the slope. This is your formal definition. Okay, we've got all this with the limit down, the f of x minus f of a over x minus a. The slope of the function at a point x equals a is the limit, and then here's your limit, provided the limit exists, which means that it's continuous and there's no broken spots and there's no gaps and there's no holes and there's no jumps and there's no removable points. If you don't have continuity, none of this works. You have to have continuity. This only is valid on continuity. So if your function is discontinuous, you can say, oh, I'm only going to work on one side of the function because it's continuous over there. I'm going to limit myself. All right, so another way to say that, instead of saying the instantaneous rate of change, it's the same expression. It's a different expression, same work. Find the slope of the curve of the parabola when x squared equals 1. It's the same. You just need to know that the wording might be different, but it means the same thing. So my slope of the curve will be the definition of the limit when I'm approaching -1 of f of x minus f of a over x minus a. So that is the definition at the number -1. All right, so f of x is x squared plus 2x minus whatever f of a is. So if I put in -1 into this equation, I get -1 back out again. So -1 squared is +1, minus 2 is -1. So Zach, maybe to answer your question there, I would put parentheses because that is a negative number, okay, over x plus 1. So then we look at what the result is, and you're going to have x squared plus 2x plus 1 over x plus 1. And I promise you, everything is factorable and reducible. If it's not, then something's wrong with your factors. So this is 0 over 0, indeterminate, which means I should be able to factor and reduce it. So the numerator factors into x plus 1 times x plus 1. This is why factoring, knowing how to factor, is going to be really important for you. Reducing and leaving me with a single factor, x plus 1. Yeah?
After you reduce those, do you want us to write out the limit of whatever again, and then whatever's left? Or could we just go right plainly?
You can go right, you mean like just sort of go like right here and then do that?
Yeah.
That's fine. All right, so I got slope of 0. That does not mean this does not exist. It means it has a slope of 0. What does a slope of 0 look like? It's horizontal. Okay, that means that this graph at this very moment happens to have a horizontal slope. What's the shape of the graph again? It's a parabola. When's the only time a parabola has a slope of 0? So what have I actually just found? I just found the vertex. I didn't mean to, but I found the vertex because it had a slope of 0. All right, now it gets good. Here gets some good algebra. Okay, we've been doing all polynomials, cubes and squares. Does it work for square roots? Okay, it has to be able to work for all of them. All right, so we want to find the definition of the slope, but notice I didn't say at what point. Can you still do it? Yeah, we're just going to call the point A, and we're not going to use an actual number. So our slope will be the limit as x approaches a of f of x minus f of a over x minus a. All right, for this problem, it is square root x minus square root a over x minus a. Which is 0 over 0 if I would plug in a. Which means this has to be factored somehow. We are very used to factoring the numerator. In this case, we're going to factor the denominator. Okay? All right, so maybe on the side, everybody knows how to factor this one, right? How does that factor? X plus 2, x minus 2. How about, does everybody know how to factor that? X plus rad 2, x minus rad 2, right? It's just the square root of whatever. Just because it doesn't work out to be a perfect square root, you can still do it. What if it was just this? Square root x plus square root 2 and square root x minus square root 2. They don't have to be perfect squares. Just because, so that's exactly what we're going to have here. We don't have a perfect square, but we can still factor. So my numerator will be rad x minus rad a. What will my denominator factor into? Square root x plus square root a and square root x minus square root a. Just because they're not perfect square roots doesn't mean that they don't factor. So then I can reduce this x minus a completely reduces that x minus a. Does that mean that the numerator has just evaporated and there's nothing left? What is in the numerator? 1 over the square root of x plus the square root of a. Then I can plug in a. And I won't get 0 over 0. I will get 1 over the square root of a plus the square root of a. And when you add two things together that are identical, you get 2 of them. So the answer is 1 over 2 times the square root of a. This is an expression for the slope along a curve. I didn't use any numbers, I just used all letters, and it still worked out fine. Yeah?
Is that like always going to be like that? So it's like if we know it's something's in a square root, it's always going to be 1 over 2, right?
You like the always things. If something is in a square root, it will be that if the thing in the square root is a single value. But if it's not a single value, it's not. So I wouldn't want you to memorize that as an always. Yeah? Yes. All right, last one. All right, it's a quotient. Do the rules still work when you're working with quotients? Yes, the rules have to work. Okay, if it's a rule, it has to work, as long as you don't break any of the other math rules here. All right, so we're following the slope of the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So f of x is 1 minus x over x. And then x approaching 1, what will that give me? If I plug 1, it will give me 0. Is that a problem? No, it's not a problem as long as I don't get 0 over 0 over x minus 1. So what I have is the awkward 1 minus x over x minus 1. Super awkward because there's 2 denominators or maybe 2 numerators if you look at it that way. So instead, whenever you have multiple numerators or multiple denominators, you multiply by the reciprocal. And so we will have 1 minus x over x multiply. Instead of divided by x minus 1, we will multiply by the reciprocal, which is 1 over x minus 1. That is all legal. But this must be reducible. If that's the whole goal, is what I'm working towards, there has to be something to reduce. And there is. If these were exactly the same, what would they reduce to? If they were the same, they would reduce to 1. They are not exactly the same. They are exactly opposites. And so instead of reducing to 1, they reduce to negative 1. So these two things will reduce to negative 1. So then I will have the limit as x approaches 1 of a numerator of negative 1 and the denominator of x. And then I can plug in the number 1, and I get a slope of negative 1.
You always put that negative 1 in the numerator?
Yes.
Or what if it was like, I guess, negative 2 or something?
And it would be in the numerator. Negative 2, yeah. Okay, so final thing. Walking out today, you should understand which 3 things are the same and how they could ask it. If they ask for the slope of a line, or the average rate of change, or the secant, then you are straight out doing f of b minus f of a over b minus a, because you have 2 points to work with. If they ask you for the slope of a curved thing, not a line, a curve, if they ask you for the instantaneous rate of change or the tangent, all 3 of those are going to need a limit as x approaches a of f of x minus f of a over x minus a. So there's 3 ways to ask for each of them. Just be watching how they ask for that, what the vocabulary is, so that you can do the math.